Welcome, everyone, to our panel on the advantages and challenges of long and short-stay missions to Mars. I'm Tim Cichan, the Space Exploration Architect at Lockheed Martin. Today, we'll be discussing the two classes of Mars missions, short-stay or opposition class, and long-stay or conjunction class. We've got a great panel here for you today. Hoppy Price is the Mars Program Chief Engineer at the Jet Propulsion Laboratory. Bret Drake is Associate Director in the Space Architecture Department at the Aerospace Corporation. And Dr. Sharmi Watkins is the Assistant Director for Exploration in NASA's Human Health and Performance Directorate. So the mission class is one of those key aspects of designing a mission for humans to go to Mars. And there's implications across the whole architecture on which class that you choose. So that includes propulsion requirements, how long the missions are, abort capabilities, and even the possibility of doing a Venus flyby on the way home. So at Lockheed Martin, we are continuing to work on our Mars base camp concepts. In papers this fall, we're going to discuss a new vehicle configuration that includes nuclear thermal propulsion to improve performance, safety, affordability, and also to provide that ability to do short or long stay missions and reduce the launch requirements for propellant. So today, our panelists are going to explain what the two classes of mission are, continuing the discussion from the last panel, how those mission classes differ, pros and cons, the different risks involved with each from their own perspective. They'll present for about 5 minutes or so. I'll ask them a few questions, and then we're going to take questions from the audience. So please put your questions in the chat. So Hoppy, let's start with you.
Okay, thank you, Tim. So in the Mars Program Office, we're currently managing 3 orbiters and 2 robotic rovers and 1 helicopter on Mars, and they're doing great things. And we would like to have humans join us there, join the robots. And so the question is, what's the best way to get there? What's the best path? And so we'll talk about the short versus the long stay missions. So go to the next slide, please. And a trip to Mars and back, it's a double rendezvous problem. You have to go out and rendezvous with Mars on the way there. And when you're done and you come back, you have to rendezvous with Earth on the way back. So the planets have to be aligned just right in order to do that. And so there's 2 major trajectory classes that people consider. On the left is the short stay opposition class. And you can see the blue arc is the trip out from Earth to Mars. And then you get to Mars and you go into orbit, and that small orange arc is your stay time at Mars, which for the short stay is around a month, about around 30 days. And then when you come back to the Earth, there's that long red spiral coming back in, and you actually go inside the orbit of Earth and typically do a Venus flyby gravity assist to help with your delta V, getting enough change in velocity to get back to Earth, and then you arrive back at Earth. On the right side is the long stay mission. You can see that there's a short blue arc going out there and a long orange arc because you're going to stay at Mars over a year, typically about 550 days. And then you have to wait till the right time to come back to Earth. And that's the red arc coming back. So go to the next slide. And the opposition missions are typically 650 days, although some years are actually longer, even as long as 800 days, but on average around 650. The conjunction class missions are around 950 days. And the opposition class missions, although they're shorter, they require typically much greater delta V, like 2 to 5 kilometers per second. So that's a lot. The opposition missions vary greatly, and many of the opportunities are not so good, and Bret will talk about that later on in his presentation. The conjunction missions are pretty consistent, and they're available every 2 years, so that's kind of handy. The robotic missions that we have sent out are typically on the conjunction class. That's lower delta V. And then, as I mentioned, the long duration missions, it's been about 550 days. The short duration are about a month. And so even though the opposition missions have a shorter duration, the actual transit time that you spend, not at Earth and not at Mars, it is longer. Most of the short straight trajectories do perform a Venus flyby, either on the outbound or the return leg. Now, 2033 is a great opportunity. and it's one that only comes by, every 15 years or so. And that gives you a 570-day short stay opportunity, 1.6 years. And the delta V penalty is lower than for other years, but it still requires 3.3 kilometers per second for the Earth return burn versus 1.1 kilometers a second if you were doing the long stay mission. Next slide. So, for the Venus flyby, thermal control is an issue. So inside 1AU, you would probably need to deploy a sunshade to provide thermal control for the Mars transit vehicle. And you need to point the sunshade towards the sun to shade the vehicle. And the solar arrays would need to be tilted to be off-pointed from the sun so that you meet their thermal control requirements. And you'd probably have to have some brief periods off sun point to do trajectory correction maneuvers, or if you had an off nominal pointing event. And if you had non-cryogenic propellants, that would make it less problematic. But in any case, the thermal control is something you really need to address for the short stay missions. So there's this risk of performing the Venus flyby for like a 1.8 year mission versus a longer 2.6 year mission that doesn't have these thermal control issues. Also, when you're inside the orbit of the Earth, solar flares could present a greater threat for the crew. So an adequate radiation shelter area would need to be provided inside the crew vehicle in the event that there was a solar flare event. Next slide. So there's actually an alternate option. If you're doing a conjunction mission, you can actually reduce the transit time by a month or more each way with some additional delta V. And so this requires less additional propulsion than if you were doing the opposition class mission. So these trajectories never go inside the orbit of the Earth, so that reduces the thermal challenges, especially for the cryogenic propellants, and it also reduces the risk to the crew from solar flares. And so if you use this approach with the fast transit conjunction class mission, the total time you spend in microgravity and in deep space radiation environments is lowest for that option if you're able to spend your time at Mars on the surface. And the surface times on Mars can be equivalent or even longer than the regular conjunction missions for this type of a trajectory. So next slide. So in conclusion, the short stay opposition missions offer advantages to minimize deep space exposure time for the crew, but with the cost of some significant engineering challenges. And some years have huge propulsion requirements for the opposition class, and some years are not even that much shorter than the conjunction missions. But if advanced propulsion capabilities are available, like nuclear thermal propulsion, or if more propellant mass is allocated for current propulsion technologies, the fast transit conjunction missions could be an attractive option for reducing the crew exposure to the deep space environment. So that's it from my presentation.
All right, thanks, Hoppy. One follow-up question. You talked about 2 to 5 kilometers per second more for opposition class and huge propulsion and propellant. And how much propellant are we talking about in that difference between opposition and conjunction class? I know it kind of depends on what propulsion you're talking about.
Oh, as far as propulsion mass?
Yeah.
So for some architectures that I've been looking at, if you do an opposition class mission, the size of the propulsion stage you'd need to put at Mars to bring you back to the Earth is something like around 50 tons or so. And if you're doing this the 570-day mission in 2033, you need something like 2 100-ton stages to bring you back. And if you're doing a year that's not as good as 2033, you would need maybe 3 of these 100-ton stages to bring you back.
Okay. So we're talking about, many multiples of launches more.
Right. And in order to get like a 100-ton chemical stage to Mars, you would probably be talking about 1 SLS launch and several commercial launches to provide all of the different propulsion stages to get that thing out there and get it positioned for the trip back.
Okay. Great, thanks. And
Sure.
yeah, we'll hear more from some of the panelists coming up about, okay, so we got propulsion to worry about, but what are we trading? And certainly the shorter missions are attractive. All right, thanks, Hoppy.
Sure.
Bret, over to you.
Okay, thank you very much. So yeah, this question, short stay versus long stay, which the conjunction versus the opposition, has been a a cornerstone of all of our human exploration architecture studies since I started, 35 years ago studying this problem. And it continues. And what I'll describe today is it's really the choice is really a discussion of the balance of the various trades. There is no magic bullet out there. So if you go to the next chart, I want to go into, Hoppy set the stage pretty good. I want to go into a little bit more detail, pulling some charts that have been shown in the public domain over the last few years. This is a recent NASA analysis done showing the variation that Hoppy talked about, across the conjunction class and opposition class. Over on the left is the variation of conjunction class. And you can see with the trajectory, dips down, we call these little fish hooks, where at the bottom of that is the optimum time to depart. And you can see that for conjunction class missions, it doesn't vary very much. There's a slight variation across 15 years that Hoppy talked about. That's called the synodic cycle. So they're fairly stable. They're lower and they're fairly stable. You look over at the opposition class missions on the right-hand side, there's a much larger variation. Whether or not you pick up a Venus swing by inbound or outbound or even at all, there's a great variation. And you see that because of that, a lot of people will focus in on the good opportunities like Hoppy talked about, 2033. That's an exceptionally good opportunity. It doesn't occur again for another 15 years. And so, 2046 or so will be another low in that cycle. So when you're choosing the mission cycle, it's from a mission planning perspective and architecture perspective, you don't necessarily want to focus just on that best opportunity, because if things don't go right, you don't have a launch cadence the way you wanted to, your technologies don't pan out, take a little longer to develop, or Congress doesn't appropriate the funds that you need, you may need to slip. And if you slip and you've only designed for that good opportunity, you'd have to stand down for 15 years before you get another opportunity. So we generally look across a broad spectrum of these opportunities and try to pick ones that are hard, but not too hard, and not too easy, so that we have an opportunity to fly these missions over various different opportunities across that cycle. So you see the variation there. NASA's kind of looking at the 2039. It's not the hardest, but it's a very challenging mission to use that to design the systems. Next chart, please. So here's another view that Hoppy was talking about, the variation of trip time versus what delta V. And the delta V is the amount of change in velocity you need to impart on the vehicle to get there and get back. Over on the very right-hand side is what Hoppy talked about, these fast conjunction missions. You can basically pinch the transit times, make the transit times to and from Mars shorter, stay at Mars longer. So the total time that you're away from Earth still is long, but the time that you're in free space getting to Mars can be shortened. And you can see that's quite a cliff you have to climb up as you try to pinch those transits out to Mars. It rises very quickly. For the opposition class missions, you see there's various different opportunities with and without Venus swing by. You can see there's a general trend that as you decrease the overall mission duration, the total delta V, change in velocity, goes up quite dramatically. And also, the longer you stay. These type of missions, these short stay opposition missions, once you arrive at Mars, every day that you stay, that geometry of getting back to Earth is changing and is getting worse every day you stay. So there's a natural tendency to want to stay as short as period as you can before you start to come home. And you see that in the variation as well. That's an example of a good opportunity in 2033. Next chart. As Hoppy mentioned, there's a great variation across that synodic cycle from opportunity to opportunity. So you can see there's a sweep of the total mission duration versus the opportunity. And you can see there's a huge variation. So again, that's another indication there that you have to, again, think across the whole synodic cycle and what you're trying to accomplish for an exploration program. And you don't want it to necessarily be a one-off type mission. Next chart. And then the question becomes, well, how does that vary as what are the key parameters that really drive the mission design? Sharmi is going to talk about the human health aspects right after I do. And there you may be more constrained and concerned about the total time away from Earth. So you may be time constrained. So if you want to fly every opportunity to Mars with a fixed duration, say 600 days, you can see there's a huge variation in mission mass. basically almost tripling the size of the vehicle from the best opportunities to the worst opportunities. So that's an important consideration of how the human health impacts the overall mission. But on the other hand, if you wanted to, say, have a constant vehicle design with the same number of launches required to meet the mission, your mission variation would have to vary quite a lot. Maybe, from the, like Hoppy talked about, in the mid-low 500s all the way up to 800 or so days. So quite a range in variation of the mission duration. And you see this is a statistical analysis that was done, that as you decrease the time and increase the delta V, there's more uncertainty in the vehicle design. The vehicle gets much more sensitive to that change in velocity, which makes other challenges for the human vehicle design as well. Next chart. And Tim, you kind of asked this question about how do all of these considerations of trip time, mission duration, stay at Mars, how do they vary for different propulsion choices? So this gives you an example of taking those delta Vs, mapping them into the vehicle designs. And you can see things like the solar electric propulsion hits a cliff fairly quickly, that it's really not suitable for opposition class missions. Chemical, you could do it, both opposition and conjunction, but you see there's a general trend of higher mission mass, which means more launches. And then both NTP, nuclear thermal propulsion, and nuclear electric propulsion have that ability to sweep through both the opposition and conjunction class missions. So it's a big understanding, trying to understand what technology you want to push, and then how it drives the overall mission choice, which drives into the number of launches and things like that. Next chart. Here's another example. Hit one more time. Yeah, this is an example from a recent NASA analysis of a nuclear electric propulsion, solar electric propulsion, hybrid concepts, where you're combining both a high thrust system to get the vehicle started for leaving Earth and stopping at Mars using a high thrust system, and then using that electric system, sort of like your fifth gear, your electric vehicle. And you see the same sort of trends, that conjunction class missions are represented off on the right, are fairly stable, long missions, low mass. But as you try to decrease that total mission time, you hit those walls fairly quick of increasing mission mass pretty quick, kind of very dramatic knees in the curve. Next chart. So the other things that you need to consider when you're choosing the mission is it's not just pure trajectory. I mean, you really need to think about what you're trying to accomplish at Mars. What can you accomplish in the short time, for instance, an opposition class mission, what you need to accomplish there. And there are, as I mentioned earlier, the trajectory considerations, how frequently do you want to go, but what orbits you go into and what you want to accomplish. Many of these missions, you pre-deploy systems ahead of the crew. For instance, the landers that the crew is going to use to actually land on Mars. You don't want to push those landers through these high delta V maneuvers. So those are usually pre-deployed waiting at Mars for the crew. Sometimes some mission concepts even consider returning, pre-deploying the return propellant. That's fine, but you need to consider getting to those assets. Generally, you capture into a weak orbit at Mars, because pushing the vehicle all the way down to a low orbit becomes very impulsively demanding. So you have to really consider the plane changes that are required for the rendezvous. That takes time, or that takes more delta V. And that eats into your time at Mars. So when people talk about 30 days at Mars, that's the total time from arrival to departure. That doesn't include the time to rendezvous with those assets, descend to the surface. Sharmi is going to talk about some of the gravity adaptation issues. And once crew is transit to Mars in 0G, they have to readapt to a gravity environment. That takes time. And so all of those eat against you in an opposition class mission of how long you want to stay and how it overall drives into the system design. So choosing a mission duration, choosing a transit trajectory is a highly coupled, interrelated design space that you really have to look at all aspects of the mission design. And then my last chart to kind of wrap up this discussion is an example from Design Reference Architecture 5, where we looked at a total trade tree of all the different major options that really influence the architecture, and then looked at what are the key characteristics of those missions. The things that really are key figures of merit, where does one mission class stand out versus another, so that you can understand the push and take, because an opposition class mission will have certain advantages, but it has other challenges. Same thing with conjunction class. You have to look at all of those interrelated issues before you can actually choose the mission choice. And with that, that concludes my introductory part of the discussion.
Thanks, Bret. Yeah, and I can see the complexity, and I can also see that, NASA and lots of different organizations have been studying how to get to Mars for a long time. And we've got a lot of work done there. And but from another option perspective, is it an either or kind of thing? Like if you brought enough propellant to do an opposition class mission and started on a nominal conjunction class, could you consider the opposition class mission to be an abort possibility?
You can, but you really need to really dive into what are the risk modes of the vehicle and the overall mission construct. Because when you talk about opposition class missions, you talk about pre-deploying or taking extra propellant to perform a maneuver off nominal. It grows very fast. You're talking about tens and, as Hoppy just talked about, hundreds of tons of propellant. So that's one option, is turn and burn. But all of those options, the return options, are not quick. It's not Apollo where you're back in a few days.
Mm-hmm.
So the failure mode is many months, if not a year or more, away from Earth to be able to come home. So the crew still has to survive. And so in a lot of those scenarios, a lot of times it's more advantageous to increase your redundancy, increase your reliability, add extra components and repairability of the system so the crew can then handle those situations real time, can still conduct the nominal mission, but take extra mass in terms of reliability and redundancy rather than just propellant to turn and burn home and still have many months to come home.
Oh yeah, that's a great point, in that we really should be thinking about a long-term expedition, and that crew needs to have all the tools necessary to deal with any contingency.
Yeah, and it's challenging. I mean, it's different. Like you're driving down the highway in your car and your air conditioner breaks down. Well, for you roll down the windows, you find the next gas station, you fix the car. Well, we can't do that. If our air conditioner fails, the crew dies. So they have to fix that air conditioner while they're driving down the highway without stopping. And so it's a whole new paradigm that we have to build into the way we actually fly and control these missions.
Yeah, so they might bring 2 air conditioners.
Yeah, well, that's exactly what we do. Exactly.
Yeah. And that might be better than bringing propellant. Okay.
Yeah.
Interesting. All right. Thank you, Bret. So next, Sharmi.
Well, thanks for having me on the panel. And I just have a few slides to share with you. I wanted to focus on some of the human system considerations as we think about these different trajectories. And when we talk about the human system, a really good place to start is with the 5 hazards of spaceflight. And so in this graphic, you see in low Earth orbit 5 icons, and those 5 icons represent the hazards of spaceflight. They were created by NASA's Human Research Program's communications team. So I wanted to thank them for letting me use the animations in my charts today. So I wanted to talk through each of these hazards, talk about what we know from low Earth orbit and what's going to change as we embark on a mission to Mars. So we can start with the icon in yellow, which represents the distance from Earth. And traditionally, as we sit in low Earth orbit, we are a comfortable 250 miles from Earth. And what that affords us is the ability to resupply pretty often. We can do fresh foods. We can do medications that are unexpired. We have almost no comm delay, very few communication blackout issues. And if we ever needed to, in the event of a medical emergency, we could be back on Earth in a matter of hours. And as we've just been talking about, as we head to Mars, that distance from Earth increases, and you saw that animation go by. The distance from Earth is going to grow regardless of the trajectory we choose, but we'll be heading away from Earth. We'll be spending quite a bit of time at a distance from Earth. Resupply is unlikely to be frequent, so we'll have to pre-supply our foods. We'll have to ensure that the medications we send are within their expiration dates or effective for the entire mission. And an important thing that we just discussed is in the event of a medical emergency, we have to recognize that timely return to Earth is not going to be possible. So we're going to stand and fight. We're going to address that medical issue either with the resources we have in the transit vehicle or with the resources we have on the surface. And so what that means really is a shift in crew autonomy. So in today's missions, ground support teams are available. We can walk the crew through medical events. We can provide real-time guidance. And you'll see that representation and responsibility flow to the crew to be their own medical providers with, of course, assistance that's coming from Earth, but maybe 20, 30 minutes delayed. If we look at the next icon as it stays there in low Earth orbit, it's a black icon with the Earth and Mars tugging at that astronaut, and that represents gravitational transitions or adaptations. And so for a typical mission to the International Space Station after the dynamic events of launch, there's an adaptation to microgravity that occurs in those first days and weeks in flight. Then the crew typically spends months on the International Space Station before doing the return leg of the trip back to Earth. And when they land on Earth, they then are greeted by ground support teams who are there to assist them as they go through a pretty challenging readaptation to 1G. As we head toward Mars, you're going to see that there's the adaptation in transit, which won't be as fast as what you just saw with any of the options we're talking about today. But then when they do adapt to Martian gravity, partial gravity, there will not be a ground team there to greet them. So the crews will have to assess themselves and determine when they're ready to do those first EVAs. In low Earth orbit, the next icon that's there in blue, it represents radiation. And we are relatively protected, as folks know, in low Earth orbit by Earth's magnetic fields. As we head toward Mars, though, we'll now enter the deep space environment, have more galactic cosmic radiation to deal with. And then on the surface of Mars, an even different radiation environment as we go into the surface radiation zone there, which is more akin in terms of the quantity to what we see day to day on ISS. Then in purple, you see an icon that represents isolation and confinement. And in low Earth orbit, we have grown accustomed to a very large space station that's equivalent in volume now to about that of a 5-bedroom home. It has the advantage also having some pretty spectacular views of the Earth. And as we head toward Mars, we know we'll be in a different environment, likely smaller than the International Space Station for transit, much likely to be smaller, at least initially, for our Mars missions on the surface. Now, we may build that up over time. So that, I think, is maybe an open question of how much isolation and confinement. Another important piece there is that we expect to do frequent EVAs on the surface of Mars, which to look at the geology, and we expect those to be very rewarding, work-intensive sorts of opportunities to leave the habitat. So there is a psychological advantage there to that work as well. The final icon that I have is the one there in lime green that represents a closed environment. And we're accustomed on the ISS to the closed environment, which is balanced by very complex life support systems to balance the oxygen and the CO2. And we take great care not to introduce, for example, microbial contamination within that closed environment. As we head to Mars, we'll have the transit vehicle, which will have certain properties. It'll be similar to the ISS in many ways, with also complicated life support systems. But then we'll have surface systems that may be very different. We may choose different pressures, different oxygen concentrations, because each of the elements of this Mars architecture will have different roles to play. And we may be balancing on the surface the risk of decompression sickness versus in transit, we may want to stay at a higher pressure. So we can talk a little bit more about those details as we go to the next slide, where we take these 5 hazards of spaceflight, and I'll start to derive for you what we call our human system risks. So these are the risks that we understand regarding spaceflight, and we look at all of these in terms of their likelihoods and consequences and consider them for each mission. So if we look at the ones that are derived from isolation and confinement, you'll see 2 risks there. One is at a team level and the other at the individual level. You'll see 4 additional human system risks that are related to distance from Earth primarily. You see inadequate human system architecture, which kind of nods to that increased autonomy that's necessary, and the risk that in the absence of those good interactions between the human and the other systems, that autonomy may be challenging. We talked a little bit about the challenges of the food supply and needing medications that are stable throughout the mission duration, and also runtime. You know, Bret talked about the different lengths of the mission, as did Hoppy. The longer we're away from Earth, the longer since your last medical checkup, the more time you have to develop a medical condition in flight. There are 2 human system risks that we look at regarding radiation. So one is the in-mission risk of non-ionizing radiation, and the other is a long-term health risk, which is associated with that radiation, and that's radiation carcinogenesis, or the development of cancer as the result of radiation exposure. We have 12 more that we consider primarily related to the change in gravitational fields. And I won't go through all of these, but we can think about maybe bone fracture as one. We know that our bones are developed to withstand the loading that our bodies experience in a 1G environment. And when we are in a microgravity environment, the scaffolding that we need to maintain here on Earth for 1G is a little bit unnecessary. So our bodies get rid of that excess scaffolding by reducing bone density, which can lead then or be a precondition to bone fracture. So we'll have to be very careful to bring with us the right countermeasures to prevent that from happening. We have a lot of experience we've gained on the International Space Station with our countermeasures about how to maintain bone integrity over time. Maybe another one, sensory motor alterations related to the change in gravitational adaptation. Our inner ears are gravity dependent organs. And so if you take that gravitational vector away in microgravity, become a little disoriented. The triggers and the sensations neurovestibularly that are happening are not in alignment with what a 1G baseline would be. And so your body learns to ignore those extra signals. So that's a challenge for us as we enter the Martian atmosphere and land on the surface of Mars. Having those crews learn to listen again to their inner ears that have been sending faulty signals to that time will be a really interesting challenge. And as I mentioned, the crew will have to do that adaptation just relying on themselves. And then the final hazard to risk box there has to do with the closed environments. And I talked a little bit about some of those challenges, but there's a risk, of course, if we kept the oxygen concentration too low, a risk of hypoxia. If CO2 is too high, carbon dioxide exposure or toxicity could be a concern. And I talked a little bit about decompression sickness, as changes in pressure as we get in the suit to go do the interesting work on the surface of Mars. There's a risk there of decompression sickness if we don't have the right pre-breathe protocols in place. So taken as a whole, those are the human system risks. And for any of these risks, we can think about the different trajectory options. We can think about what these risks look like cumulatively over the transit time. Some of the risks are going to be more significant during the transit phase of a mission. We can also look at how these risks stack up for the surface stay. Generally speaking, the human system risks, we're going to be additive as we add the transit and the surface stay, and shorter durations may be overall less risky from a human system perspective. But there are some subtleties there. There are some of these risks that would be more responsive to a partial gravity environment. That would be a countermeasure for some of them. A good example for that might be the spaceflight associated neuroocular syndrome, which is a relatively new finding we've seen that is a change to the structure of the eye that causes some vision problems. Our leading theories today are that that is a cause of fluid shift. And if it is fluid shift, then the period of time we spend in a partial gravity environment may be therapeutic. So it may be better to have a short transit, some time on the surface of Mars to readapt, to have those fluids shift toward the feet again before re-embarking on another transit. For radiation, of course, cumulative dose. The surface of Mars is a lower radiation daily dose than it is in free space. But of course, we have to add all those pieces together and look at the overall mission. And I mentioned for in-flight medical conditions, the longer the mission, the more opportunities you have to develop a new condition. So those are some of the risks that I wanted to touch on to give you a sense of the trades that we will be making as we look at these different trajectories.
All right, thanks, Sharmi. So one question I'm curious about is that on the radiation risk, is it a risk about issues during the mission or issues cropping up later after the mission? And how do those two risks compare? Like, is one worse than the other, or that sort of thing?
Right. So we've been looking at that pretty extensively. And the bigger driver for us is that long-term health risk. So the cumulative dose over the course of a mission and what that does for someone's lifetime chances of developing cancer. So we have experts within the NASA community who have been looking at that, who set the standards for what would be an acceptable risk to take on for these missions. And traditionally, and what we've been looking at lately, is a lifetime development of cancer of less than 3%. So that your additional days and time spent in space, kind of taken for a vulnerable person or at around the mean, would give you no more than a 3% increase at your lifetime chances of having a cancer, whether that be a solid cancer of the organs or leukemia, so a liquid cancer of the blood.
All right, thanks.
Sure.
Well, thanks to all the panelists for interesting presentations there. Questions are coming in from the audience. I'll get to those in a moment. I've got a couple of my own. First question, I think, to Bret. The previous panel talked about space nuclear, both from a propulsion and from a power perspective. What are your thoughts about the promise of space nuclear, and is it necessary to go to Mars?
Well, the more advanced propulsion you have, the better for Mars missions. I mean, Mars missions are hard, and so the more thrust and ISP you can get, the better it is. But you also have to consider how it ripples through the entire architecture. There is no free lunch, as I mentioned before in my briefing. And for instance, the NTP, it's a great high thrust, high SP system. For those of you who don't know about it, it's a solid core reactor where you just pump hydrogen through it and it produces thrust. Well, its best ISP comes with hydrogen, and hydrogen is hard to store. It takes up a lot of volume. It requires some advanced cryofluid management. So it becomes a challenge there. Nuclear electric, on the other hand, requires a large change in temperature. So you need large radiators from the reactor in order to drive the electric motors to actually drive the thrusters. So as much propulsion you can get is advantageous. If you fall into that opposition class mission discussion, where you're pretty much set that we need to do an opposition class short stay mission, you pretty much fall into that advanced propulsion concept bailiwick. You need advanced propulsion, and that generally needs nuclear. If you are willing to add a few days, say 90, 100 days to your total mission duration, and go switch over to the conjunction class, where you don't force the trajectory, but you wait for proper alignments to get there and come home, you probably don't have to have nuclear propulsion. You can probably get away with chemical aerobrake, or even the solar electric hybrid type of concept I talked about earlier. So it really depends on what you're trying to accomplish and how all these integrated risks then drive that decision. So it's advantageous, but I wouldn't say it's absolutely required unless you go with short stay opposition class missions.
Great, thanks. Sharmi, we've got a lot of experience now on ISS, and in particular, a lot of work over the years on mitigating zero gravity. And every time it seems like we understand a problem, another one pops up. I think that's to be expected. But given that ISS work, both what we've done and what we're planning to do, what's the level of risk from zero gravity given appropriate mitigations like exercise?
That's a great question. We do have a suite of countermeasures that we have a lot of experience with today that gives us confidence that in that transit period, we will be able to mitigate the risks that I described to human health and performance. Maybe the most robust countermeasure suite that I could pull on as an example would be our exercise countermeasure suite. But of course, you know that we have the advantage of having lots of launches to the International Space Station to build out and have that pretty robust suite, which involves 3 different pieces of hardware. For a Mars mission, I hope that we'll be able to condense the different tools we have in our tool belt into a single machine that we can have that can be low mass, because I know we have to do our part. But the idea there would be to provide not only aerobic, but resistive countermeasures for things like bone density, for the risk of muscle loss. It can provide benefits from a sensory motor perspective in terms of just that cadence of the footfalls and practicing that ambulation to get them ready for Mars. So that's an example, I think, that's pretty robust. It probably won't be those same 3 devices that we take with us to Mars, but we'll take everything we learned from those 3 to have a really nice device that can provide all of those benefits from a Martian perspective. I should also point out that we'll need more than one set of devices, right? So we need something for transit, and then we'll need our surface assets as well. So I think you were focusing in a little bit on the microgravity piece, but that's an example of what we have there. Also learned a lot about what it takes to live as a team for those long durations of time with lots of great analog experience. But an important thing is, just private crew quarters. You're spending all this time with a small crew. You do need this ability to go and have some space that is yours. So private crew quarters in the transit is another countermeasure we would want to see. Tools for circadian entrainment are also important. We'll have the advantage once we're on the Martian surface of seeing, something like a Earth circadian rhythm. I know it's a little bit longer. We'll get those extra 30 minutes in. But in transit, we need to mirror our body's circadian rhythm. So we can do that with countermeasures like lighting, making sure there's adequate sleep. Those are some of the key lessons we've learned from ISS that we would want to feed forward to the transit and also ultimately to the surface.
All right, thanks. Hoppy, when you were presenting, you mentioned something about the Venus flyby and needing to off-point the solar rays, and it got me thinking about, the Venus environment's very different, and why would you want to have less power? But you were talking about off-pointing the solar rays because of thermal concerns?
Right. So the thermal arrays that are designed to work between Earth and Mars, if you just point them straight at the sun at Venus, they're just going to fry probably. They'll fall apart. So typically on our planetary missions, when we go into Venus and Mercury, we will often intentionally off-point the solar panels, like by 45 degrees or even 60 degrees. And it's okay because the total amount of power we're getting out of it is fine. You're taking a cosine loss, but there's so much more energy from the sun. So you'll be getting the same amount of power out of the arrays, but you intentionally off-point them so that they'll survive the thermal environment.
Oh, great, thanks. Okay, let's get to some of our audience questions here. Two trajectory questions came up. One was, are these Hohmann transfers, the conjunction and opposition trajectories, or are they something else? Maybe that's for Bret.
So the conjunction class missions, LongStay, if you really optimize for a minimum type energy, then that's essentially a Hohmann transfer out there and then back. Opposition class missions, no, you're a brute force. It's not Hohmann. You're just trying to optimize the trajectory given the constraints within the mission that you're designing.
Okay. And then Hoppy, is there a free return option anywhere here like we have for the moon?
Sure. For most of the conjunction class missions, you can set it up so that when you're going out to Mars, if you are not able to do your Mars orbit insertion burn, you could fly by Mars and be on a free return trajectory to come back to the Earth pretty much in the same time frame as if you'd done the whole mission. So it's still like a 950-day mission, but you can be on a free return. And I believe you can also do that for the 2033 opportunity, which is the 570-day mission, because the trip out there is basically a conjunction class trip going out, but you're taking an opposition class coming back. So I think you could probably do the free return setup for the 2033 mission.
Well, that's true if you design it to be the outbound trajectory to be exactly units of 1 Earth year back, and you're going to come back to the same spot that you generally came by, unless you're using Mars to kind of bend the trajectory. So you have to bias the trajectory from the beginning, which means generally more propellant just to protect for that free return. Yeah,
that's true. And if you did the free return in 2033, it wouldn't be a 570-day mission. It'd be more like a 900-day mission.
Right. So you have to plan for that. Your habitat has to be.
You have to have enough consumables, food, all that stuff.
Right.
And that brings up the topic of going to Mars without going to the surface? Maybe this is a question for all three of you. Do you see value in either a orbit mission where you go into Mars orbit, or one of these free return before we do the landing?
To me, if you wanted to do a first mission to Mars, and let's say, for example, you're doing 2033, and you could do a short stay mission and just do an orbital mission, that would retire the risk of your system for going out to Mars and coming back, and the crew wouldn't be away from the Earth for such a long time, and you could prove out your transit habitat and your operations and communications at Mars, and it gives you the opportunity to do an earlier mission before you've had the money and the time to develop a lander. So, just as Apollo 8 happened before Apollo 11, it might make sense to do a first mission as an orbit-only mission. But I think that is a lot better if you can do it as a short stay, because a long stay mission, if you're going to be orbit only, you're going to be orbiting Mars for 550 days, and that's probably not going to be great for the crew physiologically or psychologically.
Yeah, so that's a good example where this debate continues, because topics like that come up, and I don't think personally that an orbital only mission really helps much in terms of buy down risk, because you're exposing the crew to a lot of risks of just getting out to Mars, never landing, and coming home. You can do those types of operations closer to Earth where you have better abort options, like around the moon. Exercise your systems, exercise your habitat, exercise your propulsion systems without having to expose the crew to the risk. It's, these missions are not like Apollo, where the Apollo 8 and Apollo 10 were along the same mission choice as the nominal missions you're going to fly later. A purely orbital Mars orbital mission is completely different in terms of a risk posture for the crew than what you would have for a normal Mars mission. Those a good example where you have to really think about all the risk posture and how does that mission actually fit into the overall testing program, risk mitigation program, and then also mission return. Now, there could be some political reasons for doing it, but from a technical perspective, I think there are better ways to retire risk than going all the way out to Mars.
Although, isn't there certainly a psychological difference and probably an operations difference whether you're doing something in cislunar space for a year or 2 or 3 and actually being at Mars and doing science from orbit and taking on that risk? I assume there's value there, and then the question is how much value.
Right. So one of the things you get from actually going to Mars and doing an orbital mission there is testing out the systems in the environment of Mars, the thermal environment, and the operations are definitely more test as you fly and fly as you test if you're actually out at Mars. And so if you I agree with all of Bret's points that there's many things you can test in cislunar space, but there's still more, I think, that you get out of actually doing the Mars mission. And there are also psychological and political aspects of actually doing the mission going to Mars.
And Sharmi, everything we're talking about is dangerous. And, part of your job is to figure out what is the right risk level and mitigations. And what do you think about, the risks of being on the surface and doing entry, descent, and landing versus the orbit only?
I think that the risk is going to be worth the reward, as folks have mentioned. I mean, to go all the way to Mars, we're going to be really excited to get on the surface and explore. I think that that's the point of going. And so I do think with the current campaign, we want to spend our time at the moon testing out systems, learning what we need to learn so that when we go to Mars, we'll be able to explore. And I think the psychological benefit will certainly be there. I think that it will be high reward for the crew to be on the surface doing those activities versus just doing a flyby. There's definitely some technical benefits, some testing that would happen if we were to do just a flyby. But from a sense of the crew, I believe that those surface operations will be well worth it and certainly add some risk, but we will be, of course, developing the systems and the countermeasures to the fullest extent possible combat that risk so we can put people where they need to be.
Yeah, and Tim, your question kind of leads into one of the lines of thinking that people have. You do an orbital only mission, well, you can avoid the interdistant landing risk. You can avoid the development of those systems, but in reality, you're delaying them. But the objective is to get to the surface of Mars, and you can't wait to do a Mars orbital mission and then say, okay, now let's start developing the lander. That's going to be a 10 or plus, 7-10-year development program. So you have to have already started the development of those lander systems before you conduct an orbital mission. And so you're just compounding the cost against each other. So it's really, what is your test program? How are you mitigating those risks? And it's not always just flying to a destination. There are other ways that you can buy down those risks without exposing the crew to those types of in-mission risks.
Okay. So one of the audience questions for Sharmi is quite to the times is, what is the risk of microbes entering that closed environment that you were describing? And are the astronauts going to need to quarantine for a really extended time before going to Mars?
So we actually have been doing that for quite some time, since even before, those early Apollo missions, quarantine has been part of NASA's policy. So it turns out that we didn't have to change much, even in this time of pandemic, about how we prepare our crews to go even to the space station. So we do have a period of time that we call our health stabilization period. We have the crews undergo some, extensive testing, and about 2 weeks before launch, we stop doing contact with folks who have not also been screened. And the idea is to reduce the chance of any communicable disease making it to the International Space Station, because we don't want to launch someone who is feeling ill, nor do we want to have the entire crew ill with something as simple as a GI illness. So I do believe there will be a quarantine before leaving for Mars. It probably won't be too different than the quarantines we have today.
All right, thanks. So one of the questions here is, could a short duration mission be done on the first mission, and maybe to set up a base for a longer second mission? Can we mix and match on when we do the types of short stay or long stay, or is it such an effect on the vehicle designs and the crew countermeasures that we can't do that?
Yeah, so if you decide to fly the first human Mars mission as a short stay opposition class missions, you're buying into advanced propulsion, large vehicles. So if you built that system, you could then switch over for subsequent missions and fly conjunction class. But in that case, you would probably fly those fast transit ones. You'd use that advantage of those propulsion systems to get to Mars faster and stay at Mars longer. So you would just use the same vehicle to fly that type of a fast conjunction mission. The question is, what's the cost and risk associated with building that larger complex vehicle, and how does it ripple through the whole launch infrastructure, mission operations, those sorts of things? And are those hurdles that you can actually get over?
All right, thanks. So we're starting to get to the end of our time. And so I wanted to ask of all of the panelists here kind of an open-ended question. We've talked a lot about the different risks that we are balancing, technology development risk, medical risk, the logistics and supplies, supporting the mission. And from your perspectives, what are your thoughts on the best way to balance these different risks, or how do we make these big, huge decisions when we're designing how to send humans to Mars? How do we achieve that right balance, and where do you see the focus of meeting the mission requirements in balancing those different risks? Why don't we start with you, Sharmi?
Sure, I think it's a great question. That's one we spend a lot of time thinking about. To me, the best steps we can take for risk mitigation for Mars are really to spend our time at the moon wisely. So there's a lot from the human system perspective that we think we can learn. either in lunar orbit, where we have a little bit more of that deep space environment from a radiation perspective. We can learn how we do in those adaptations to partial gravity. And of course, it's different fractional gravity, but we believe that there may be some similarities in the way the body responds. And we want to build our N. Right now, we have an N of 12 for the moon, right? So we'd be very happy to have more subjects, a very diverse population going to the moon to better understand at that basic fundamental level what's going on with human physiology. Because when we improve our understanding there, I think we can have more robust mitigations, both for the transit and for the Martian surface. So to me, that's our biggest chance to improve our posture before heading to Mars.
All right, thanks. Bret?
Yeah, I was going to say almost the same sort of thing. I think part of the challenges associated with Mars missions is when you look at the systems, the capabilities required, the technologies, it looks like a daunting task. And if you add them all up, people look at it and say, no, there's got to be an easier way. But if you do things right, we're already starting down the process of building our launch vehicles, building our crew vehicle, building a gateway. We're starting the early concept development on what an Artemis base camp will be. And if you do that right, that can be a very good down payment on your Mars missions. A lot of your surface systems, your habitation systems, your rovers, power systems can all be Mars prototypes. Your operational concepts can start to exercise how you will do it on Mars. And then when you go and look at, well, what's left to do Mars, it's the hurdles are much smaller. And the bite in the apple has to be smaller. So I think that's one of the best ways of doing it. Also, there's some commonality across the systems where if you start developing those systems early, you can use them regardless of the trajectory choice. So you find that low-hanging fruit, start the development on those systems, and then let the systems evolve so you actually make the mission trajectory choice.
Right.
Yeah, I agree with everything that Sharmi and Bret said. And, as Bret was mentioning, you have some systems that you can use at Mars. And I think if you develop the big thing to me is the transit habitat, getting the crew to Mars, getting them back safely. And, if you use different types of propulsion systems, I think you can still preserve that transit habitat. So if you started off doing missions to Mars with one type of propulsion system, and then a more advanced one came along to enable you to do better missions, faster missions, you can keep the same transit habitat, but use a different propulsion system. And then as far as risk, I think one of the things I worry about as a spacecraft engineer is just the complexity of these systems and how long a Mars mission is. So, we can envision great advanced technology systems that may have wonderful performance, but if they're very complex and they have a greater risk of breaking down or not lasting the mission duration, then I think we have to think very carefully about that, because to me, crew safety is primary. That's more important than the performance that we get. So, if you have to launch like another, 200 tons into Earth orbit to get a less complex system, but to do the mission, if it's safer for the crew, it's worth launching the extra mass. So it's all a trade-off of complexity versus a risk versus performance.
All right. Well, thank you, everybody. We addressed a lot of different risks here. I was kind of getting worried, but I heard that optimism at the end. And I think the main message here is complexity is the enemy. And probably very excitingly, given the state of the Artemis program, all of the things that we are doing at the moon is really a dress rehearsal for Mars. And that's super exciting. Artemis 1 is going here within the year. So off to Mars we go. Thank you, all of you, for an excellent discussion. Thank you to the audience for supplying great questions. And we'll see everyone next time.